Here's problem 1219. The diagrams below show forces of magnitude F applied to an equilateral triangular block of uniform thickness. And which diagrams is the block in equilibrium? Let's look at the first one, A. These forces have moment arms. All of them have moment arms, let's just say column R, of perpendicular distance from the axis to their line of actions. Here's line of action, like this. So they all are trying to make this thing rotate clockwise with these moment arms. And so they're all positive torques. So the summation of the torques about the z direction is going to be greater than 0. There's going to be a net torque on this block. So it's not in equilibrium, does not apply, because there will be a net torque. Alright, let's look at B. The line of actions of these forces now go through the origin, all three of them. They have no moment arm, and hence the summation of all the torques about Z will actually be equal to 0. So we have torque equilibrium on this one. What about force equilibrium? Good question. Well, if we look at these forces, all of them F, these two forces coming off here from the horizontal are going to be coming down at a 30-degree angle because they're bisecting the 60-degree angle on the side of the triangle. So we are going to have a component in the x direction of a f cosine theta here being offset by the same magnitude f cosine theta going in negative x direction. And then we'll have two components in the y direction going down, both of them f sine theta. So we're going to have a 2f sine 30 degrees going down being balanced by an f going up. In other words, the sine of 30 degrees is 1/2, and 2 times 1/2 is 1. So we are going to be balanced in the y direction with a f versus a f force. So the summation of all the forces in the y direction will be 0. Summation of all the forces in the x direction will be 0. We have no net torque. We have no net force. This particular configuration is in equilibrium. Let's look at C just to make sure. We have F going down, F going down, F going up. There's 2F going down, 1F going up. The summation of all the forces in the y direction is going to equal a negative F, at least in the J direction. So there is a net force down, and hence this is not in equilibrium. Alright, let's look at the last one. We have a force F going to the right, force F going to the left. They're going to cancel out in the x direction, but then we'll have a force unbalanced in the y direction. So the summation of the force in the y direction will equal F, which is not equal to 0. So we have we have a net force, and net force here. So not in equilibrium based on that either. And we could make the same argument. Well, actually, in this one there is no torque on this last one, but we do have this net force. So because there is a net force, there is not equilibrium. And on the previous one, the torques cancel out as well, so there's no torque here either, because we have a moment arm here and a moment arm here, and those torques cancel out. And then we have one force go through the middle with no moment arm, so no net torque, but we do have a net force. So equilibrium only in answer B.